We encounter series systems when considering multiple performance levels and multiple load combinations for a structure. Let's take up the multiple performance levels first, and here is one such schematic for a dual performance level situation. So this diagram is a bit detailed, so let's go through this part by part. On the right part, you see the C delta relationship. So we can think of delta as being a response, and C is some measure of capacity. So it's a nonlinear relationship, and what we have plotted here is the median curve between C and delta, which means that if we ran this process again and again, we would get several stochastic processes, and what you see there is the median line. So from this median line, we could obtain the yield capacity corresponding to some displacement delta predetermined. We could get the yield capacity, which we call, let's say, Cy, and it would have its mean or median that's indicated in terms of MCy. We have the density function, which is indicated as PCy, and other metrics if you like. MCy is the median. We could also define the design value CYD, typically less than mean, a sort of conservative value. So we could define those quantities for yield. We could also define the ultimate capacity also from this force deformation type relationship, and that's what you see on the top, marked in the green circle now. And likewise, as was in the yield, we can define the density function of Cu and the median ultimate capacity MCu, the design ultimate capacity, and so on. So now, with that in mind, let us look on the left side of the figure. So if we have two levels of capacities for the same structure, it's quite reasonable to suppose that we would consider those as acceptable limits under different intensities of loads. So for moderate loads, we would be more interested in yield and or the structure does not yield, and for high loads, extreme loads, we might be more reasonably interested in the structure doesn't collapse, it doesn't fail. So this density of the yield capacity Cy should, it seems, be compared with an ordinary type of load. So that's what you see on the left, marked in green circle, is the density of the ordinary load. L being the load, that's the L axis, and L0 is the ordinary load, PL0 is the density function, and there you can define its design value and compare it with the design capacity and make sure that the two match, and thereby the design can be satisfied. Likewise, the ultimate capacity is relevant when we have extreme loads. So on the L axis, we can define L max and its density and its design value, and compare it with the design capacity and satisfy a design. So this gives an idea about, for the same structure, we can be interested in two or more performance levels, set different requirements, which would also be governed by different regimes of structural mechanics. Maybe for yield or below yield, we'll be happy with linear analysis, elastic analysis, and for near ultimate, we would probably need to consider beyond yield behavior, plasticity, nonlinearities, and so on. And we see this sort of thinking in modern design codes. For example, this is an extract from FEMA 350, and you see that there are two limit states or performance levels: the immediate occupancy and the collapse prevention. And each of these has a very different demand level, different set of requirements, both for non-structural and structural parts. So, for example, the demand for immediate occupancy is a 500-year return period earthquake, whereas for collapse, the demand level is much higher at 2,500-year return period. And you can read the other aspects also, and it's clear that the performance levels are different, the expectations are different, the demands are different, and presumably the acceptable safety should also be different. We can look again from FEMA 273. There is another example. There are 3 levels now instead of 2. There is immediate occupancy, there is life safety, and then collapse prevention. And each of them have different limits for the maximum inter-story drift ratio, IDR, and you see how they increase with more intense and more severe limit states. So from 0.007 to 0.025 to 0.05. So with these in mind, we can define a very small example, and let's see if we can learn something from this. So let's say we have a structure which is acted upon by 2 sets of loads, dead and maximum live load, and the second being dead and ordinary live load. And under the maximum live load situation, the structural capacity which is relevant is CU, and for the ordinary live load we have CY, C yield. And the requirement is that the structure must not collapse under 1, meaning the load combination or the demand 1, and it must not yield under 2. So 2 different sets of expectations. We have here all the distribution information of the 4 random variables, CU, CY, 5 random variables, CU, CY, D, LM, and LO. O being ordinary, and M being max. So under the assumption that all the random variables are mutually independent and just for the sake of simplicity each is normally distributed, we can find out what the reliability index is for each limit state. And it's an interesting exercise. Is there any dependence, any correlation between the 2 limit states, between the 2 safety margins? So if you would like to solve this problem yourself, please pause the video, or I'm going to present the answer in the next slide. So here they are. We define 2 safety margins, MU and MY, and you see how they are, just the linear combinations, and each is normal with their own mean and variance. And with the given numbers, we can find that the mean of MU is 60 and the variance is 25.7 squared, and the mean of MY is 20 and the variance is 7.48 squared. These, I hope my numbers are correct. And now with this, one question was, what is the correlation coefficient between the 2 limit states? So we find the covariance and divide that by the 2 standard deviations, and the answer is almost 0. It's about 2.1%. So because D is the only common random variable there. If there was dependence between the CU and CY, there would have to be a strong case for that, but then we would probably see more higher correlation coefficient between the 2 safety margins. And finally, the beta values for these 2 limit states, which is mean divided by The standard deviation, it's 2.33 and 2.67 in ultimate and yield respectively. Now, whether these are adequate, whether we should have a higher safety margin in ultimate, obviously is a very valid question, and we will like to take this up towards the very end of this course in part D. Let's move on to the next related problem under this topic is two load combinations. So we discussed two performance levels. Now let's have two load combinations, and let's say the resistance is common in both these two load combinations. So we have dead plus maximum live load, and the second load combination is dead plus ordinary live load plus maximum wind, and the structure has to survive both. Here you see the all the random variables. Again, there are 5 of them and R being common, so one could expect that even though all these 5 are mutually independent, that there would be a good amount of correlation between the two safety margins. So the first question is we need to find the reliability in each of these two load combinations, and the question B is find the correlation coefficient. And as before, we take the 5 random variables to be normal with the mean and COV as given, and each are they're all mutually independent. There is one typographical error. The LM has a mean of 40 kilonewton, not just 40. Anyway, so if you want to work through this, then please pause the video. Otherwise, let me present the answer, which is this. M1, the first safety margin, is a normal with mean 40 and standard deviation 19, so that gives a beta of 2.1, and M2 is normal with mean 40 and a standard deviation of 13.6, and beta 2 is 2.9, and the correlation coefficient between these two safety margins is 0.4.